Goedemiddag.
Goedemiddag. All right, let's get started. Welcome to our second C-Roads Antwerp-Helmond seminar. Please note that this session is being recorded for the benefit of those who couldn't attend today but would like to view it later. As you know, since the start of this year, the European Union has mandated ISA, Intelligent Speed Assistance, in all new vehicles. Let's delve deeper into what this means. First, Laura Kama from Tractable will provide an overview of our C-Roads project. Next, Niels Kneppers from Vitron will explain the workings of ISA, its current state in Belgium and the Netherlands, and future developments. Following that, Johan Hellemans from Unix Traffic will share practical examples and insights from our project. We suggest that you note any questions you may have during the presentation in the meeting chat. We will have a Q&A session at the end where these questions can be answered. I now give the floor to Laura.
Good morning. Welcome everyone to this webinar. My name is Laura Camacho. I work for Tractable, the company in charge of the general coordination of the C-Roads Antwerp-Helmond project. The project is co-funded by the European Commission and is framed within the broader C-Roads platform. The C-Roads platform is a joint initiative of EU member states which can count on participation of local authorities and road operators from different countries in numbers. 50 cities in Europe are part of the platform, and today already 20,000-kilometer roads are equipped with short-range CATS services, while long-range CATS services are provided on more than 100,000 kilometers of the European road network. Next slide, please. So the overall aim of the C-Roads platform is the testing and implementation of CATS applications in a way to ensure cross-border harmonization and interoperability across member states. This is achieved through a series of initiatives and projects, starting with the development and publication of common technical specifications alongside with intensive plans for cross-border testing to verify interoperability. Interoperability is based on standards and protocols under the ETSI, combining ITS G5 and operational cellular networks. Next slide, please. The C-Roads Antwerp-Helmond project is framed within the C-Roads platform and is focusing on local applications and interoperability testing of services in Belgium and the Netherlands. The project has a duration of 2 years, and our consortium consists of 9 partners, you see mentioned on screen, spanning from local authorities from both Antwerp and Helmond to infrastructure and technology providers active in the 2 countries. Next slide is the project involved rollout of different applications in both Antwerp and Helmond, but also on the highway connecting the 2 cities. Pilots tested within the project covered 3 categories of CATS applications. So first, next slide, please. First of all, we have Advanced Driving Assistance Systems, or ADAS. Of ADAS application, the project focused on intelligent speed assistance, which this webinar today is about, as well as real traffic information to assist the driver through both the installation and operation of onboard units or the use of mobile apps, in our case, Flitsmeister and Trackmeister apps. Next slide. A second category of application tested and implemented within the project is UVR, Urban Vehicle Access Regulation. So different applications of UVR were tested in this project, including access warning and limitations for trucks, time-sensitive speed restrictions such as those in application near school areas, or even speed restriction for active mobility users in urban slow-speed zones. Next slide, please. Finally, so different mobility services were also tested in the context of the C-Roads Antwerp-Helmond project. Of the mobility services we tested, I would like to mention truck buffering and Trackmeister, park and ride information to vehicle drivers in Flitsmeister, and traffic light priorities for both trucks and bicycles, and Trackmeister and Sway applications. Next slide again. To conclude, this project then focused on the deployment of combined Day 1 and Day 1.5 CATS in Antwerp and Helmond. The rollout of services in the 2 countries allowed us to test and verify the interoperability of the services themselves. And through the project, evaluation of all these services mentioned encompassed not only pure functional aspect, but we were also able to assess their impact, including the acceptance from the user perspective. And finally, we are also developing scalability and implementation strategies for the different services tested within the project. So next slide, please. In terms of timeline, as I mentioned before, this project has a duration of 2 years. It started back in November 2022 and is reaching its final stages with the finalization of all activities and deliverable scheduled for the end of October next month. And next slide. Today, my colleagues will talk to you about ISA services and the first of the 2 webinars that are organized by PXL in the context of this project. So next webinar will take place next week, October 1st, and we'll dive into traffic light prioritization services. But now today I will leave the floor now to Niels Kneppers from Vitron, who will talk to us about ISA.
Yes, good morning. Well, my name is Niels Knappers. I'm project leader in Vitron, and from that side also active in this project. So I will now explain something of what we did during this project. But to first start an explanation of what is actually ISA, so the Intelligent Speed Assistance. We have a short video that kind of summarizes it in a way. Oh, I see that the sound is not coming from it, but there is some subtitles. Yes, next slide, please.
Great.
Well, as you kind of saw in the video, the ISA system, as we also developed within Vitron, is a kind of speed limiter to the vehicle, which basically in all regular vehicles you can now see on the road, we can retrofit it and build the system in. And it kind of works in the way that you have, it works on both a digital map, so you can see it as a map with all the known current speeds applicable on the roads. And there the GPS sensor of the system compares, of course, its own location with the speed in the digital map and can then limit the vehicle on that maximum speed. So the driver cannot overspeed in that sense. Another input of that one is the vision sensor module. And as you can also saw in the video, that is just scanning traffic signs on the road. And taking over the maximum speed signs and limits also the vehicle on that. It's kind of the redundant, the backup system of the digital map. So it also works then in cases such as roadworks warning, roadworks and other temporarily speed restrictions. In the project, we used two data sources, which will be explained later. In the Netherlands, it was from the NWP. And in Flanders, Belgium, and Antwerp, in that sense, we used it from the Open Data Portal Antwerp and Flanders Open Data. That is kind of the inputs that go to the ISA processing and logging unit. So that decides when and at what speed the vehicle needs to be limited. And that also logs all the actions and events are taken. So every sign that is detected is also logged at locations with current speed. We can also see if the driver overruled the system. So what you can see in the last part of the video, if he presses the throttle fully for 2 seconds, you can still overrule the system, but it then gives an event in the logging. So we can use that for analyzation afterwards, and also see if the digital map is actually up to date and yeah, can be well used for the ISA system, or that there are discrepancies with reality. What we then did and tried out besides these two main forms, let's say, of limitation during this project is the combination with CITS. So what we had there was an onboard unit, our own onboard unit, which is capable of receiving messages via so the cellular pod as ITSG5. That receives the message from a roadside unit. Also, we have some examples that can be shown later. And that can be, let's say, the third input to the system. In this project, we did not actually limit the vehicle because there were some, let's say, concerns in trust of the messages, because we do not know who is sending them out in the future. So we now tend to not limit the vehicle actually, but inform the driver on the HMI, so that the display before the driver to what speed it should drive. As you can also see in the diagram, from the ISA processing and logging unit, we send a signal to the speed limiter that is installed in the vehicle, and that actually caps the maximum speed, and on the HMI, so a screen what we also developed ourselves, the maximum speed at that moment is shown, as well as the other messages coming from the onboard unit and via the CITS path. Next slide, please. Yes, next. So what we did also in this project regarding the ISA part is that we updated the digital maps, which I will explain a bit. We improved the HMI. We improved our log file so it can be used better in the future. And we introduced an ISA feedback loop to make the data better in that sense for the ISA application. Next slide, please. To start with, we now take a look at the ISA, let's say, backend data of the Helmond use case. So that's the same for the whole Netherlands with our system. We retrieved the data from the National Road Database, the NWB, which is in that sense frequently updated, but still have discrepancies with the reality. Not every municipality or road authority updates the map as often as it should, or not all the speed limits are accurate or corresponding reality. What we do to make our system, of course, work the best is we continuously retrieve the latest version of the NWB map, ensuring the best possible driving experience and the most up-to-date data. However, even then, there are some discrepancies, so not all the roads show on the digital map the right speed, and therefore we introduce the ISA feedback loop, which I will explain in a bit. Next slide, please. Then we have the data from the Antwerp use case. So that's one of the two cities in the project. We first tried to use the open data from Flanders itself. However, that was with initial testing already found not to be the best quality data. There were a lot of discrepancies with the reality. The speeds were not matching the real speeds. So we decided there to make a mix of two different or three different data sources. So to have, let's say, the best of both worlds in city Antwerp, but also on the highways and the main roads in the rest of Flanders. This took some quite extensive data processing, simulation, and physical testing on the go. But that worked out very well. We also demonstrated during the project, and that in that sense enabled the cross-border functionality of our ISA system. So we can now seamlessly drive from the Netherlands to Antwerp without any interference in the ISA system or its functionality. Next slide, please. As I discussed before, what we found in the initial data set was that there was some discrepancies more than we have found in the Netherlands with data quality. Also, driving in the city center of Antwerp, we encountered new scenarios in that sense that we haven't found or tested before, such as tunnels, viaducts, and crossovers, which made it very hard to let the vehicle choose, let's say, in what road it was driving. So what happened oftenly was that we were limited to the wrong speed in that city. That's why we also in the project, which was initially one of the goals, did not fit it in private vehicles, but we did some extensive testing and retrieved valuable data from it. Next slide, please. One of the other developments we did in the project was to improve our HMI. As you can see in the pictures, the top two pictures were our ISA system as we started with it, which only showed the maximum speed at the location. That is, in that sense, of course, working fine if you only have the speed. But what we now introduced was the CITS link, and there you want to also show additional information to the driver. That's why we developed a new HMI, and it can be seen as the picture below, where we also show next to the current applicable maximum speed also the warnings that are generated by the IVI and denim messages, as will be explained later. It's improved visibility. It can also be in dark mode. We get sound warnings, textual warnings, and instructions, and we can toggle, let's say, the system on and off, or have additional settings via the screen instead of only showing it. Next slide, please. Then what I said, we improved the logging, and that is an important thing to make the system better. So with the logging, we can in one way see how the drivers are performing, what are they doing, and as you can see, there's a small example of the log file that we have, and where we started with and what we added to this project were, let's say, the fat black parts of the ISA log file. So therefore, we added these in order to make a better estimation or better analysis of how good the location mapping actually is with the HDOP. Next to that, we also show the icons, numbers, and let's say the type signs, so we can also compare it with the real life infrastructure, if it's correct, if we see the right signs, and we can better tell if there is something wrong with the system or that signs actually on the road do not correspond to the digital map. Also the previous speed limit and an alternative speed limit, which is mainly applicable in the Netherlands. By example, on the highways here, we have it on certain time zones on the highway that you can drive 100 kilometers an hour, and after a certain time you can drive 130. That is also added, so also on the digital map we can now choose based on time what speed is applicable. That can in the future, by example, be used in school zones. And of course, the digital, the current GPS speed to see if people tend to stay at the maximum speed or indeed overrule or not, or what the drivers are doing at specific routes, which might be interesting also for the local road authority to see how the roads are used. Yeah, next please. Then we introduced what I said, the ISA feedback loop, and that is mainly because we found out both in the Netherlands already before and in Antwerp, Flanders, in that sense, that the data of the digital map is not always corresponding reality. So what we now tend to do is to create a feedback loop where the signs physically on the road are scanned by the vision sensor. These are logged, and this log file can then be analyzed and automated to see if there are discrepancies to what we see on the digital map as a current speed and what the vision sensor sees on the road. And there we can also find that what you can see on the right, that there are also on the digital maps from other sources such as Google, but also the NDW itself, do not correspond to reality with the signs on the road, as by example, the Helmond signs. So road authorities now can see the differences between what is logged and what is physically on the road and on the digital map, and then decide if they need to update the map or check if signs are missing, if the speeds are wrong on the digital map. And in that sense, they forward that data back to the NDW, which then can update the map, and we download the latest version of the map. In that sense, by driving around, we can update the digital map and make it better for future use for all sources. Next slide, please. Yes. In Antwerp, we also did the same, because the previous example was then in Helmond. In Antwerp, what we said, the data was not of that good of quality that we trusted it to build it in private vehicles in high numbers. So we installed an ISA system which was not limiting in a taxi in Antwerp. As you can imagine, they drive a lot of kilometers within the city center and scan the traffic signs on the road there, which then can be compared with the digital map of Antwerp. We found a lot of events, scanned signs, and logged files in that sense, which in that way can also be used in the ISA feedback loop for Antwerp City. Next slide, please. Well, now we only tested it with a couple of vehicles, in the Netherlands with a bit more, but this is what I said, the ISA feedback loop, and it also had the advantage that it's not only helpful for us, but also users can see progress based on their own data in their own city. So the more you drive, the more you scan, the better the map can be updated. In that sense, the whole ISA development can be accelerated if road authorities choose to drive with these systems and update their own maps based on the log files. It's not only Vitron that is helped by this data, of course, because also all other ODMs, and as you saw on the previous slide, there were also other navigation apps, by example, that partially use this data. As and showing the wrong data. Dus the more signs are scanned and the map are updated, the more companies and OEMs, etc., favor this. And in the end, contributes to safer roads in the city. Yeah, then I think Johan will explain a bit between the ISA and CITS use cases.
Yes. Hello, good morning. My name is C-Roads Antwerp-Helmond. I'm responsible for CITS within Unix Traffic. Next slide. For those who don't know Unix Traffic, we provide intelligent traffic solutions. We operate and maintain more than 1,500 traffic controllers in Flanders, Brussels, and also Wallonia. And we also provide traffic management centrals, parking guiding systems, tunnels, and waterway monitoring. Next slide. CITS provides useful interaction between infrastructure, like, for example, traffic lights, but also on the other side, the road users like cars, but also emergency vehicles, active road users like pedestrians, cyclists. The Traffic Management Central is there to collect, process, and share all this information and to distribute it to all road users. And two main technologies are used for distributing standardized CITS messages. On the top, we see the ITS G5, also known as Wi-Fi P or short-range communication. It makes use of dedicated roadside units, which have to be put alongside the road, and the vehicle should be equipped with compatible onboard units. This technology is, for example, already built in more recent car models. So these messages distributed by ITS G5 can already be received by a lot of vehicles, but of course also by the onboard units that Vitron has built into the cars. They're compatible with this short-range technology. It's ideal for use cases that need high reliability, like emergency use cases, and also for self-driving vehicles, it's the more preferred reliable technology. On the other hand, below, there's the 4G, 5G cellular communication, sometimes 3G. It's preferred to have 4G or 5G, and this is called the long-range communication. It can make use of dedicated infrastructure, but it can also be just like an app on your smartphone. It might be a bit less reliable, but the fact is a lot of people have smartphones, so it's much easier to roll out and also to do pilot use cases, tests, and for example, shared bicycles, for example, they could have this built in. And then we can also provide CITS use cases with shared mobility services. Unix provides the infrastructure and services for both short-range and long-range CITS solutions. Today we focus on short-range solution. Our CITS clouds can connect to other ecosystems like mobility data provided by Flanders, but also other data sources like traffic management centrals. We try to be flexible in getting a lot of information from different parties and to share it with the road users. What we also try to do is we enable cross-region CITS use cases. So not only we not only focus on Flanders, but we have also done projects to enable CITS bus priority with Le Tech in Wallonia, also with the LAN in Flanders. We have a huge amount of traffic controllers in city of Brussels, where we also enable bus priority use cases. We've done fire truck priority for city of Antwerp. And of course, in this C-Roads project, we cooperate together with Landis, gemeente Helmond, and city of Antwerp. Okay. What have we done specifically for this project? With combination with Vitron to enable the ISA use case, we provide RSU, but we had to open it up to enable it to talk to different ecosystems. So we connected it to our CITS cloud. so that it allows us to generate the EVIM messages and the denim messages in a flexible way, that we also have additional logging. For example, on the map, you can see the vehicles that are detected over short-range technology. Yeah, we can have a lot of statistics from all of the messages. So specifically, the tunnel height warning use case in Antwerp, wherever there are tunnels, there's problems with vehicles being too high and still trying to drive through tunnels. Also, City of Antwerp has made a lot of effort in the past to warn upcoming drivers about the height of the tunnels, but still regularly in the news we see a lot of messages of vehicles crashing into tunnels, damaging the infrastructure and also creating traffic jams. So by doing this use case, we want to show that it is possible to warn the vehicles in another way. On an onboard unit, really dedicated on this location, they can see this message. Niels will show this later on in a video. And also, maybe later on, it can slow down the vehicles proactively when they really are too high and they're entering the tunnel. So in general, we placed an RSU close to the Jos Brabant tunnel, and it is broadcasting the EVIM message, which contains a detection zone and it contains a relevance zone. So the detection zone is where we first give a warning to the driver, where they still have the option not to take the tunnel. So they get the warning up front. At the moment, they can still choose not to take the tunnel. And it's the onboard unit, in this case of Vitron, that actually does the comparison between the broadcast with the specific tunnel height and the current height of the vehicle. And so it's the onboard unit that chooses whether or not to display the warning to the driver. And then, of course, the relevance zone, that's where the tunnel height, the height is restricted. In the future, this might be the zone where we really want to slow down vehicles so that they really notice something is needs their attention. Okay, you can see the details of the message on screen, but this is standard ETSI EVIM messages. Yes.
Yeah. Then for our side, let's say the on-vehicle side, a small explanation of the onboard unit. So we received the messages from the roadside unit, such as Johan just showed. We have our own feature hybrid onboard unit, which is capable of transmitting and receiving messages via short and long range, and can be easily installed in let's say, the test vehicles that we used. The messages that we can use here and can be functional in the use cases are COM, denim, IVIs, and spot and map for the closer use cases later. We have our own backend that can connect to various long-range and short-range services, such as also, in this case, Unix. And yeah, we receive these raw messages, just as Johan just explained, and we make a kind of readable format for it and send that through to our ISA system, which then on its own turn shows it on the HMI. That is also demonstrated in Antwerp and both Helmond with the use cases roadworks warning and tunnel height warning, but it is applicable for all the IVI and denim messages. Next slide, please. So that's actually then the combination between the CITS and ADAS, so the ISA link, which is also an ISA ADAS system, and CITS. And we looked at what use cases could be implemented with the current ISA system, with the focus on the actualities and importance in both Antwerp and Helmond. And that's why we also chose to do the tunnel height warning, since it was a tunnel, what Johan said, what this crashed into a lot. So that took our interest, and now we demonstrated this use case there. Next slide, please. But we now demonstrated with the tunnel height warning, which is IVI message, and roadworks warning, which is a denim message. There are only two, but we can also show, in that sense, all the use cases which are listed in this slide. Next slide, please. So what I said, it was the roadworks warning and in both Helmond and Antwerp, and the tunnel height warning then in only Antwerp, which these are the icons that's also shown to the driver. Next slide, please. These are all the functionalities that we could show and can, let's say, extend to in the future. Next, please. One of the things that we, let's say, did conceptually, so not demonstrated real life, because in the project there was no traffic light operator in that sense available to send these messages to us via Johan and Unix in that sense, but we did look for the possibilities to combine ISA and GLOSA. So that's the green light optimal speed advice, where we get the traffic, the information about the phases of green, red, and yellow, and the timings to that. So then we can get a speed advice to drive what speed you need to do to cross an intersection during the green phase. These are also future use cases that we want to explore to actually limit vehicles then to that advice speed, so it improves the traffic flow. And that would be shown as on the below picture. This is then the ISA roadworks. Sorry, next one. Yeah. This is then the ISA roadworks warning with the icon on the screen, which also counts down the limit, the distance to the actual roadworks, and the code you can see on the right is the message that we received from Unix in this case, and will be shown in a short video afterwards how we implemented it. Next one. Yes. There's a kind of long introduction, so maybe we can speed it up a bit. But what you can see here is that we just drive in the vehicle. It's 30 kilometers an hour according to the map, and that is also where the vehicle is now limited to. So we're now driving in Antwerp towards the Jos-Brabant tunnel, which Johan mentioned, and we're now close to the relevance and detection zone, of course, of the message. So we now show the message of the roadworks warning towards the driver, and the same is applicable for the tunnel height warning. And we now still give the option to the driver to and so we can give the driver the opportunity to take a left or right in order to take a D route. It's a bit small, but you can also see this small triangle below the roadworks warning sign that is showing the distance to the actual roadwork zone, and will disappear, of course, afterwards you drive past it. Yeah, next slide, please. Then the other one is the tunnel height warning. Previous. Can we go to the previous slide?
Previous slide?
Yes, please. Yes. This one shows then the tunnel height warning use case. So we now see the maximum height of the vehicle shown to the right of the 30 sign, of course, and that is also in the Jos-Brabant tunnel with the actual 2 meters 19 as maximum height. On the right again, the message that we kind of show or make from the message that we get from Unix, which is just a regular IVI message. So now we implemented, let's say, the tunnel height, but in the future we can do with all possible IVI messages. And the same counts, of course, for denim with the roadworks warning. And then followed again by the video of the use case. So here you see indeed the warning popping up that you drive towards the tunnel with 2 meter 19. Also, what Johan said, this is now just implemented as a visual warning and to the driver. So watch out, you're driving towards the tunnel. The things that we want to test and explore further in the future is actually limiting vehicle speed, or maybe even come to a standstill before you reach the location. further development and research in that sense is still needed to see how we can actually send these messages to vehicles that are only too high and not stopping, of course, all the vehicles receiving the message. Yeah, they receive it. Then go to the next. Now we're driving across the parallel road, of course, so missing the tunnel, and then the message also disappears. Next slide, please. Yeah, I think Laura will take this over. Correct. Okay, I will do the lessons learned slide, sorry. Some of the, let's say, summarize the lessons learned of this project also regarding the ISA is to ensure that the centralized digital map is accurate, prioritize data accuracy and continuous map updates. So establish a clear data quality standards and guidelines. Now it's kind of to the best knowledge of the road authorities, but if there are proper guidelines to it, it might improve also future work in this. Implement automated data validation and verification. So including a feedback loop as shown before might speed up the improvements of the digital map and therefore make it also a better ADAS system. Enabling real-time updates to the digital maps. At this point, we still do it manually with research done to do it over the air. If over-the-air updates can be passed to the ISA systems, they are always up to date with the latest digital map and can also share their logging, of course, over the air to improve and speed up the ISA feedback loop. And of course, encourage collaboration among all other data providers and not only the ones that we now used for the data portal of Antwerp and Flanders, but it counts for all countries and the whole Belgium and the whole Netherlands, of course. Then the improvements and optimizations to the ISA are required in the following areas. What we found out indeed is in Antwerp, we have the tunnels and bridges problem with the layered signage. A digital map is, let's say, a 2D map, so we do not know the height of certain passovers or tunnels. Therefore, if you continue only focus on the GPS and digital map, it doesn't know on which road you are, which causes problems in showing the different or the wrong speeds. I think is at the end of speed limit restrictions at dynamic traffic signs, so let's say green arrows, but also temporary roadworks, etc. At this point, what happens a lot is that there are no end of restriction signs. In that sense, we do not really know when roadworks are over or not. So that is something that should be improved also on the roadside in the future. And expanding then the ISA indeed to include the sound signals and actually stop commands for the vehicles that's applicable in use cases such as the tunnel height warning. And of course, facilitate seamless collaboration and trust establishment. Now we can receive in that sense ITSG5 messages or cellular messages for all the denim and IVI use cases, but as we are not sure how trustful these messages are, if they are accurate and from who they are that we receive, we now choose to not actually limit vehicles or stop vehicles. We want to have a trust domain in order to be sure that we receive the right signals and only then want to interact with the vehicle with it.
Okay, thank you for the comprehensive explanations of ISA, Niels and Johan. I don't know if there are some questions in the chat we have to answer.
Yes, there's one from Chris Peters about the measures that should be taken to really roll this out. it's the ambition of the Mobilidata project in Flanders to connect a lot of data sources to the CITS ecosystem. But nowadays, the tunnel data is not there yet for all the tunnels. But together with City of Antwerp, we really want to continue with this project and to see to create have the digital data for the tunnel heights and to put them enter them in the Mobilidata ecosystem, so they can be used by different partners on not only the short range use cases, but also other use cases could make use of this data. So that are the next steps. Of course, also a lot of vehicles in future generations, they will get more and more this CITS short range on board. So hopefully that will help too. These are the things that are planned, but yeah, still a lot of things that need to happen.
Are there some more questions? Okay. Then I would like to thank you for your presence, and I hope we will see you next week in the second webinar of our project. Thank you. Bye.
Okay, thanks.
Thank you. Wij zijn er weinig over. Ja.
Ja.
Je kunt best leaven ook, omdat het wordt opgenomen. Hè?
Ja. Even, ik ga de opname stoppen.